section 3.3, which talks about properties of functions. I did send out the lecture notes again, and part of that's because there are so many pictures that we need. So the first thing we're going to talk about in terms of properties of functions is increasing versus decreasing. And you would want to know this, especially if the function is possibly, you know, representing the profit of your business or something like that. You would definitely want your profit to be increasing or getting bigger and not decreasing, although you might want your overall overhead to be decreasing. So there are reasons why you would want an increasing or decreasing function. The important thing to remember, and this is what's so vital to this, so very important, is that we are going to always write the interval in terms of x values. Never y values. And you'll see why in just a minute. So what I'm going to do is I'm going to put 3 small graphs on the board. So the first graph is going to be doing this. These are on the handout itself. The next graph is going to be looking like this. And then the third graph is just going to be a horizontal line that looks like this. And so each case, this is x and this is y as normal. Now, the technical definitions for increasing and decreasing are in your textbook. They're also on that handout. I tend to not like to write them down because I think they're much uglier than they need to be. So what we're going to do instead is talk about this from a practical point of view. So as we move on this first graph from left to right, very important, always left to right, and just like you read a book and just like we read a function, it's always left to right. We're going to notice that this first graph is going uphill. If you were a little bug walking along it, pick your favorite bug, walk along it, you'd be going uphill. And because it's going uphill, we're going to consider it to be an increasing function. So along the length from whatever x value this is to whatever x value this is increasing because you're going uphill. So from the next picture, we can see that as we move from left to right again, we are going downhill. And that makes it a decreasing function. And again, left to right is really important. So what about the last picture? Well, as I move from left to right, because it's horizontal, I'm not going uphill and I'm not going downhill. So this is what we consider to be a constant function in terms of the picture. So to help us out in terms of writing those intervals, what we're going to do is we're just going to come in and mark on the graph an A, and over here would be a B. So wherever this is at, this is B. So this is increasing, starting at A and all the way over to B. So notice it just involves the x values and only the x values. Now, for this example, it's easy to see why I'm using parentheses because this was drawn with open circles. But the theory in terms of calculus, which most of you are headed into in one form or another, is the fact that if I stop either here or here, I'm not going up or down. So when I stop on the side of a hill, I'm not going up or down. So that's why they'll always be written with parentheses. So not only will we always use the x values, we're always going to use parentheses. So over here, if we do the same thing, A to B, we're going to say that this is decreasing over the interval of A to B in terms of the x's. Now what's really happening is that the y values are what's getting bigger and bigger and bigger because these y values are getting larger and larger and larger. And over here, the y values are getting smaller and smaller and smaller. So that's when you write those intervals, you only use the x values because we already know what's happening to the y values. In terms of a constant, it would look the same way, believe it or not. So we're going to say that this is constant over the interval from A to B. So always use parentheses, always pick up the x values. And we will do some more examples of this in a minute. Again, the technical definition is in the textbook or on that handout I passed out. It's up to you whether or not you take a look at it. So that's one of the properties of functions that we take a look at. Another property we take a look at is the maximums and the minimums. Is everybody okay? I can erase?
Yes.
Okay. So we're going to talk about local maximums versus local minimums. So again, what I'm throwing at you is a lot of math vocabulary, and it's all tied into these sections here. So getting used to the vocabulary is part of what you're doing. So the idea of local means within the given picture. So for us, local means within the given picture. So in other words, you're going to be showing a picture of a graph. We're going to ignore what happens at the ends, and what we're looking at is specifically within that local given picture. So to help us out, we're going to draw two quick pictures again. We're going to have one of them that looks like this. This time we're going to be a little bit more specific about where we're at. We're going to call that an x value of c. And we'll have one that looks like this, making sure it sticks to my pictures. And x value of c. Over here, if we're inputting c into our function, then this would be f of c, the corresponding y value. And you could do the same thing over here. You'd have an f of c. So we have two pictures. They're functions because they pass the vertical line test. What we can see is for the first picture that if we walk along it, it goes from increasing to decreasing. So notice that the type of uphill and downhill changes. And it changes at this point, C. So C is really where it goes from increasing to decreasing. So by the technical definition that again is on the handout or in your textbook, this is a local maximum. It's the top of the hill. It's the peak. Top of the hill. It's a peak. On the other picture, what you're going to notice is that this graph goes from decreasing, walking downhill, to increasing, walking uphill. So that guy becomes a local minimum. It's the bottom of the valley or the trough. So in other words, on my first picture, if I am standing here, I am standing at the highest Y value on that picture. On the second picture, if we're standing down here at the bottom of that valley, we're standing at the lowest or smallest Y value. So the idea of maximum and minimum is pretty easy to grasp. You're either at the top of the hill or at the bottom of the hill. The one thing you want to be really, really careful about is that the maximum itself is the Y value. So the max is the Y value of the point. Same with the minimum, it's the Y value. And on the homework, it's pretty specific about how you type these things in. So it's going to ask you to find the local maximum. They're looking for the Y value. And then they're going to say it occurs at what X value. And we'll do that here in just a minute. But okay, any questions or comments about local max and local min? As I noticed, I ran off the board. Sorry about that. Okay, the other thing is your book does bring in, and this is in this edition, they didn't do this in the older editions, the idea of absolute maximum or minimum. so what that means is if you take a look at the picture that you are given, what is the overall highest point and the overall lowest point? So for my first picture, we could see that this would be the absolute min. So I'm going to abbreviate that as ABS, MIN for min. Whereas this point over here would be the absolute max. Sorry, not that one. This local min up here is also your absolute max. So within the given picture, what's the overall lowest point and the overall highest point? They do not have to occur at the max and mins. You only have one of those, and I will not quiz you on that again. So it's on tonight's homework, and that's it. So the easiest thing to do is to go to a specific picture and then try and pull the information that they're asking for off. So I'm going to finally start in on some examples. So example 1 gives us a picture. And again, this is where we'll spend our time drawing pictures. So 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have a point that's over here at -4, -10. I have another point where I am crossing the axis at -5. So that is -5, 0. I'm going to cross the axis at -1, 0. And we have a point at 1, 5, 5, 1, 5. And then 4, 0. And then this thing is going to dead end at 6, 10. And I didn't go up high enough, but you're right up. 4, 6. Okay. So it comes in and it's a nice gentle curve. And believe it or not, we will eventually graph this kind of stuff. Okay. So if you didn't print it, I'll give you a minute. Our leftmost point is -5, 0. You've got a bottom down here at -4, -10. You've got another point at -1, 0. Another point at 1, 5. A point at 4, 0, and 6, 10. And let's go ahead and call this point where we're crossing the y-axis 0, 4. And we're going to ask a bunch of questions about the graph again, just like we did yesterday. So there's our picture. So the first thing we want to know, what's our domain? And again, I'll use capital D for domain. So what's the domain of this graph? So from left to right, what do we got? Anybody?
Negative, is it -infinity to 6?
Beautiful. Yep. -infinity to 6. That is correct. What's our range? So where's the bottom of the graph? Where's the top of the graph?
-10 to
Yep, -10 and then up to 10?
Yeah.
And we'll use brackets on both of them because they're closed circles on both of those points. Wonderful. And again, that's on the homework that's due tonight. You do have 2 more sections due tonight. Don't forget that. But that's the first 2 sections. We've already lectured on them. Okay, part C is asking for the intercepts. Okay, so let's go for the x-intercepts first. And again, they're given to you. They're labeled. So we've got 3 of them. So we've got one at -5, 0, -1, 0, and 4, 0. And then you also have a y-intercept, and that's at 0, 4. So by now, pulling that information should be kind of second nature because you've done quite a bit. Okay, D is the new part. We want to know where it is increasing. Intervals. We also want to know, party, I'm going to tie in, is the decreasing intervals. So where is it decreasing? Where is it increasing? So what I like to do is to do these 2 parts together. Remember, these are X values only, and that's the key to remembering it. You've got to think about this. So X values only. I just literally start on the left side of the picture. So my left side of my picture in terms of x's is way out there at negative infinity. So as I'm walking along this, I'm walking downhill, and I'm walking downhill all the way until x equals -4. So I'm actually going to start here with the decreasing interval and say from negative infinity to -4, parentheses everywhere, we're walking downhill. So that's this piece that's walking downhill. But once I reach -4, I'm no longer walking downhill. I'm going to start walking uphill. And I walk uphill all the way over to 1. So to an x value of -4 to an x value of 1, we're walking uphill. So -4 to +1 is where we're walking uphill. Once we reach an x value of 1, we're going to start walking back downhill again. So now we're going to go down here to the decreasing and go from 1. And we walk downhill all the way over to an x value of 4. And then once we reach our x value of 4, we're going to walk back uphill again all the way to 6. So we'll say from 4 to 6. And again, everything written is an x value telling you where it starts and where it stops. And the only thing missing is a symbol between these two intervals. And because this is both of these things going on, we're going to put a U for union in there. And again, I have a feeling that you don't have to type that in. They're just going to give you blanks for this to happen at. So by the time you're all done, you should be able to walk along the entire picture using these intervals, telling what's going on. So again, notice from -3 to -4, that end point becomes the beginning point for the next interval, from -4 to 1. And then at 1, we stop increasing and we go back down to decreasing. So that end point becomes the beginning point. To 4, that end point became the beginning point all the way to 6. Okay, notice I didn't have to stop at those x-intercepts, so even though they're labeled as points, they're got stopping the up and down of the increasing and decreasing. So once you get the hang of it, it's fairly straightforward and fairly quick. But boy, getting you guys to recognize their x values, and these are intervals, not points, is a little difficult. Any comments about that? Part F for this picture is asking us for where it's constant. So it's asking for the constant intervals. Well, for our picture, it's never constant. We don't have any flat lines anywhere on this one. So we're just going to say none. It then goes on to ask about the local maximum. So we want to know within the given picture, where is a peak or the top of a hill? Well, I start off high, I go down, I come up, oh wait, here's the top of a hill. So for us, we're going to say the maximum value, max value is, and now I'm going to pick up the y coordinate of 5, and it occurs at x equal 1. So I know the highest point within this region is a 5, and it occurs when x equals 1. And then somebody should usually stop and ask me a question, well, what about that 0.6, 10? Isn't that a maximum? Well, by definition, it's not, because it's not the top of a hill. You don't go back down on the other side. So this is not a local max or min because it doesn't go back down. So it's kind of sneaky. They asked for the local minimum. So this is part H. I'm getting a little low on the board, so I'm going to come way back over here. Local minimum. Okay, well, in this case, we're going to have 2 of them because I have 2 valleys where I have the bottom of a valley. So one local min is, so local min is, we're going to say -10 because that's the bottom or the y value. And that occurs at x equal -4. And there's also a local min. And that one is over here at 0. And that occurs at x equal +4. Now, I'll be honest, if we were in a classroom, I would just have you guys write these as points, because in the calculus sequence, that's how you're going to write them, as points. But your textbook does not write them this way on the online homework. So they do this instead. Okay, does this picture, and it doesn't ask it on the handout, but does this picture have an absolute min or an absolute max? So I got a little bit of room over here. So just as a comment, there is an absolute max of 10. Actually, no, I'm sorry. There is no absolute max because this side of the graph continues to go up. There's no absolute max. So we're going to say none. There is an absolute min though. We have a bottom, we have a lowest Y value possible. So this Y value over here is the bottom of the graph no matter what happens because this is going to keep going up. So the absolute min is going to be, is that -10 at x equal to -4. So again, no absolute max because the arrow on the left side is going to continue to rise. So we don't have a top to this graph at all. Okay, so there's one of them. And again, eventually we will learn to graph these. This is in chapter 4, so it's not that far away. It's a nice, smooth, continuous polynomial curve. So it's a pretty graph. We'll learn how to do it though. Comments or questions? We're going to do one more. Do we need to do one more? Are you guys good or you want to do another one?
I'm okay, but
Everybody okay?
Yeah, I'm good.
Okay. Well, then we'll skip the next example. I don't have to watch the clock to make sure I'm filling all of the time here. That's kind of nice. Okay, the next thing they talk about is symmetry. So functions and symmetry. Okay, so if you remember from chapter 2, we had 3 types of symmetry. So we had symmetry to the y-axis. And I'm going to pick on our friend, that U kind of shape. So we had symmetry to the y-axis. We also had symmetry to the origin. We didn't see a lot of that. We'll do something that looks like this. And then we also had x-axis. I'm going to use this picture. Okay, so there are 3 graphs that have the symmetry that we've already talked about. Okay, well, in this chapter, we're no longer looking at just graphs of relations. We're looking at graphs of functions specifically. So because we're dealing with functions, that means over here, the symmetry to the x-axis is no longer going to happen. We're not going to see it. It won't happen again. So this over here, even though it has symmetry, is not a function. So we're going to ignore it from here on out. So it's not a function. It doesn't enter into today's conversation other than to say it doesn't happen. Okay, well, what about these two? Well, both of these pictures are functions. They're going to pass that vertical line test. They are good to go. But because we're in the function world, all of a sudden we're going to switch gears and not call it in terms of symmetry. What we're going to do instead is talk about this in terms of even versus odd. So if you have symmetry to the y-axis, we're going to consider this to be an even function. So symmetry to the y-axis tells us that it is an even function. It means it folds across the y-axis. We'll show you in a minute where that word's going to come from. In terms of the origin, instead of calling it symmetry to the origin, in the function world, we're going to call it an odd function. So we have even and odd. The way to remember them is both origin and odd start with the letter O, so that's why you can put them together in your brain. As a quick example for the 2 pictures that we've got drawn on the board, this first one would be the graph of x squared. And we'll pull this back into play tomorrow. But for now, we know that this is a quadratic. Quadratics, when we graphed them back in chapter 2 just by plotting points, gave us these U-shaped pictures. Now, when you take a look at this function, f of x is equal to x squared, don't we notice that that exponent is even, hence the term an even function. So the word even is very logical. Hey, this guy, we didn't really graph too many of, but you did graph it in the 101 class if you came through that. This is x cubed, x to the 3rd power, and you can plot some points and figure it out. You can plug in a 0 and get a 0. You can plug in 1 and get a positive 1. Plug in a -1, -1 cubed is -1. So you get those points, and we will do this tomorrow. But you can see that the exponent on this function is odd, which is why this is considered to be an odd function. So the words make sense. But just like when we did symmetry, you won't always have a picture. Sometimes you're going to have the function itself. So we need a test for even versus odd. So the test is if you plug in a negative x, and remember that's what we did with the idea of symmetry. We replaced x with a negative x and y with a negative y. But because we're stuck in the function world, we're going to have to write it with function notation in terms of the test. So f of negative x is equal to the original function. So when you plug in a negative and you have no change in the function, it is even. If you plug in a negative x and you get the opposite of the function, then it is odd. And if you get any other combination, it's neither even or odd. So this is why when we started on Monday, we had to do both a negative x and we also looked at the opposite of the function, was leading us up to this concept today. So what we're going to do is a couple of quick ones. So without graphing, we want to test whether it's even, odd, or neither. So I'm going to leave my little test written over there. So I want to determine algebraically whether they're even, odd, or neither. If f of x is even, odd, or neither. Okay, so this is example 3. Part A, we're going to do f of x is equal to 3x cubed plus 5. 3x to the third plus 5. So based on our previous discussion about exponents, you probably have a fairly decent guess on what's going on here, but we need to be careful. So what we're going to do is, to test this, we're going to come in and plug in f of negative x. So we're going to replace all the x's with a negative x. So that would be 3 times the negative x cubed plus 5. And now we'll do the arithmetic. You take a negative number and cube it, doesn't it stay negative? So I'm just going to transfer the negative out of the parentheses and move it all the way out front. Okay, so I'm done with the mathematics behind it. Now I need to take a look at what's going on. So in order for this to be even, it would have to be the same. So if it were even, it would be the same as the original. Okay, it's not. We can see that one of the signs is changed. So that tells me that the function is not even. In order for the function to be odd, it has to be the opposite of the original. It has to be the opposite. Well, wait a minute. Is this result the opposite of this one? Well, no, because if I ask you to change the sign of the function, you would also change the sign of the 5. So because the 5 is not negative, we didn't touch the 5 at all. This is also a not. So it's not even and it's not odd. I know we just said a few minutes ago that if the exponent is odd, it's an odd function. The problem is what this plus 5 is doing. We're going to see tomorrow that this plus 5 is shifting the graph, and that shift no longer folds across the origin. So because of the extra terms, I can't just look at exponents. So there's some sneaky stuff going on. So this particular one is neither. And that's my final answer. It's not even and it's not odd. It's neither. In other words, it has no symmetry to the origin and it has no symmetry to the y-axis. That was sneaky. Let's do another one. I don't think you'll have any problems with the ones that are polynomials, meaning a bunch of successive terms. I think if you're going to struggle, it will be with the ones that are rational functions where x is in the denominator. So we're going to go do one of those really quick. I'm still leaving my test over there just as a reminder. So our part B of that example is f of x is equal to x over x squared minus 1. x over x squared minus 1. And I want to know whether it's even or odd. So I'll do the same thing. I'm going to come in and replace the x with a negative x. So that puts a negative x in the numerator. I'm going to put a negative x, which I'm going to square, minus 1. So that leaves a negative x in the numerator. When I square that x, it's going to become a positive x minus 1. And then what I'm actually going to do is pull the negative that's in the numerator out in front of everything and write it as a negative fraction. Now that's pretty subtle, and I'm hoping everybody catches it. So in other words, what I'm saying is if you have a negative 2/3 as a fraction, you can write it as a negative 2 in the numerator. You can write it as a negative 2 on the bar. And if you really wanted to, for some reason, you could write it as 2 over negative 3. So all three of those are equivalent fractions. It's just a matter of where you write that negative, whether you want to write it in the numerator, on the bar, or in the denominator. So why am I doing that? Because I need you to realize that when I compare this to the original, that it is the opposite of the original. We're saying, here's the original function. This result is the opposite of that original function. So because we ended up with the opposite of the original, we know that this is an odd function. So if I were to come in and graph it, it would have symmetry to the origin because it is odd. Okay, so you have a couple of these to do. I think they're the hardest thing on the homework. They're not going to take long, but just sit back and think about what you're doing. Any comments about even and odd? It's nice because it ties in with something we already did. We're good? We're quiet but good? Okay, the last topic in this section. There's a lot of different things that's kind of disjointed if you ask me, but they just throw it all together. Is average rate of change. Average rate of change, which I will abbreviate as ARC instead of writing it out every single time. So ARC stands for average rate of change in my world. Okay, so for a curve, so for any curve that we can draw, and we'll do lots of different curves, the average rate of change, average is, sorry, that's really sloppy, is the slope of the secant line connecting 2 points. Okay, so in order to understand why we need the concept and what the concept is really saying, we're going to draw a picture. And again, it's on the handout. We're not going to be really exact here. I've got a point over here that's at -6, -7. I have another point that's at 2, 4. So those are the only 2 points that are labeled. And the graph is doing something like that. Again, what it's really doing doesn't matter. All we need are those 2 points. So that's a pretty curve. What the average rate of change represents, first of all, we're going to draw in something called the secant line. Again, this is a calculus concept, but the secant line simply means it connects any 2 points on the curve. So I'm going to connect this point and this point in a straight line like that. So this is the secant line. Again, secant line simply connects 2 specified points on your curve. The average rate of change is the slope of that line. You know, slope is a concept from a previous course. We know that by definition, it's the letter M, and it's y2 minus y1 over x2 minus x1. So using the same notation that we used in chapter 2 when we did the distance formula and the midpoint formula, we're using that same notation at the first point and the second point. So the slope of any line can be found by taking the difference in y's and putting it over the difference in x's. So for us, we're simply going to find the slope between these 2 points. So that average rate of change is going to be equal to, I'm going to do y2 is 4 minus y1, which was a -7. Be really careful about the sign. Over x2, which is 2, minus x1, which is a -6. So 4 minus a minus 7 gives me 4 plus 7, which is going to give me an 11. 2 minus a minus 6 is 2 plus 6, which is going to give me 8. So the average rate of change is 11 over 8. So 11/8. I could take it into a decimal. Why would I need to know this? Well, let's go back to the idea of your business again. And if this is how many units you sell, and this is your profit based on how many units you sell, then isn't this average rate of change telling you whether or not you are increasing between these 2 points in time or decreasing in between these 2 points of time? So the average rate of change has a lot of impact in terms of economics and in terms of growth. The thing that should be obvious, hopefully, to everybody is that if I picked a different 2 points, I would get a much different secant line. So if I picked a point here and a point here, I get a slope that looks like that instead, which is different. I could also pick a point here and draw in a secant line and get a negative slope. So depending on which pair of points you pick is what you're going to see in terms of that. So now that we have one on the board, what we can do is come in and write a formula for the average rate of change. So I think you're better off remembering that it's just a slope. So I can draw a curve that looks like this. So this is going to be A. This would be a point F of A. Over here, we're going to have B, and this would be F of B. So here's F of A, here's F of B. So again, what I'm saying is that this is the point, comma, F of B, comma, F of B, and this is the point A, comma, F of A. Now, just a few minutes ago, it was a lot easier because we didn't have the notation in there. We just had numbers, so it was easier. So the average rate of change is defined to be the change in Y. So that would be Y2, which is F of B, minus Y1, which is F of A, all over B minus A. And believe it or not, that definition right there will lead you into your calculus sequence quite well. So you take something like that, you do a couple other things to it, you end up with a wonderful thing called the derivative, which gives you an instantaneous rate of change. So it's kind of fairly powerful. So again, it simply means that for the secant line on the curve, that the slope of that secant line can be found using that formula. So on the homework, what they're going to do, they're not going to give you the specific points. They're not going to label those points for you at all. They're just going to give you a function. So let's go do one of those. So this is our last example. This is example 5. We just did example 4. Find the average rate of change of f of x equals negative 2x squared plus 4. And we want to do that for part A. We're going to go from 0 to negative 2. Okay. So from 0 to negative 2. So instead of giving me a picture and telling me points on the picture, they're just giving me x values. So these are x values. So the very first thing we're going to do is we have to come in and evaluate those x values in the function. So I'm going to plug 0 into the function, and then I'm going to plug negative 2 into the function. So I have to plug both of them in. So because they didn't give me the points, I need to go find the points that are on the curve. So plugging in 0, right back to where we were on Monday with plugging things in. 0 squared is 0 times negative 2 is 0, so we're just going to get a 4 out of that. Here we'll plug in the negative 2, and I need to be really careful and not get so sloppy about things. So it's a negative 2 times a negative 2 squared plus 4. So cleaning that up, the negative 2 squared becomes a positive 4 plus 4. So that's a negative 8 plus 4. And again, order of operations, square it, then multiply. We're going to end up with negative 4. I got a lot of 4s floating around here. So what we're saying essentially is that this translates into the point 0, comma 4. This translates into point 2, comma negative 4. And now that I have the 2 points, I can go find the average rate of change. But we had to figure out those y values first. So our average rate of change, and again, the order I subtract them in is not going to matter. I just need to be consistent. So I'm going to use this as my second point. So I'm going to pick up the -4 as my y2 minus my y1, which is 4, all over x2, which is 2, minus x1, which is 0. So again, I have this -4 minus this 4 over this 2 minus this 0. So now we're down to the arithmetic. That's a -8 over 2, which is going to give me a -4. So if I were to graph this and plot these 2 points, I would see that the slope of that line connecting these 2 points together is a -4. So it just tells me what that slope is connecting those 2 points. Comments or questions about that?
Makes sense.
Okay, then we're going to do one more and call it good. And it's just because I want you to see that depending on what you pick as your x values, impacts that slope. So for part B, same function and everything, but this time we're going to go from an x value of 1 to an x value of 4. We're going to go 1, 2, 4. So we'll do the same thing again. These are the given x values. These are the x values. So we're going to do f of 1. That would be -2 times 1 squared plus 4. Again, squaring first, 1 squared is 1. So that's just -2 plus 4, which is going to give me 2. And I'm going to plug in f of 4. Okay, I've done all the work. You go figure out what f of 4 is. So go do the arithmetic and tell me what the end result is for f of 4.
-28.
Correct. That's what I got to. Did we good with that? Thank you. Nicely done. Now we can go find our slope. So again, this translates into the point 1, 2. This is the point 4, -28. And now we'll go find our average rate of change. So it's the change in the y values. So that's a -28 minus the 2 over the change in the x values. So that's 4 minus 1. So -28 minus 2 over 4 minus 1. So that's going to give me a -30 over 3, which sure enough gives me a -10. So it's still a decreasing slope, but it's much steeper at -10. So between these two x values, all of a sudden our curve has gotten a lot steeper in terms of the curvature. So, and that's average rate of change. It's really important when you head into your calc because you're going to springboard off of that to develop the idea of a derivative. But for us, we just do the average rate of change. And that's everything in this section. Any other comments or questions?
No.
Okay.
We're all good? Okay, so don't forget 3-1, 3-2 are due tonight. It's Wednesday. You've got 2 more sections due on Saturday and the quiz on Sunday. So have a great day. Enjoy it. Stay cool. Stay out of that heat. Have fun.
Bye.
Hey.
You too.
Bye-bye.
Have a good one.